Hello, I'm Parlani, a PhD student at Radboud UMC, and in this video I'm going to talk about the next generation of multiphoton microscopy to resolve single cells deeply in live tissue. Two-photon or multiphoton microscopy has emerged as a powerful tool for intravital studies in many fields. The advantages include 2 to 3-fold improved penetrance in thick tissues, compared, for example, to the confocal, up to approximately 1 millimeter of image depth, but also the ability to record the behavior of living cells over time and the possibility of monitoring the changes of the tissue structure and the molecular processes. The phenomenon of two-photon excitation relies on the simultaneous absorption of two photons in a single quantized event. So these photons display double the wavelength and half of the energy of a single exciting photon. As an example, GFP, which is normally excited in the blue range at around 400 nanometers, can also be excited by two simultaneous near-infrared photons of around 800 nanometers of wavelength. So the photons need to simultaneously excite the fluorochrome in one single event within few femtoseconds. So high photon density of around 1 million times higher than the one used for the single photon excitation is needed for this to happen. This means that only in the focus the photons are dense enough so that two photons can excite the same fluorophore at the same instant. The good thing here is that the density of the photons dramatically decreases above and below the focal plane, so no out-of-focus background fluorescence is produced. As a consequence, a second advantage is phototoxicity and photobleaching phenomena are much lower outside of the focal plane, and all these results in an overall deeper tissue penetration. Another advantage of the multiphoton excitation is the possibility of combining fluorescence microscopy with other detection modes, including the higher harmonic generation, which allows label-free imaging of tissue structures, like, for example, collagen, muscle fibers, and lipid membranes. Here you can see an example of a multiphoton microscope. As you can see, it is as big as a room. The laser path is on the hydraulic table, and in this case the microscope has two systems for the parallel acquisition by two different users. There's a heat stage where the mouse lies during the acquisition, and the mouse is kept asleep by the continuous administration of isoflurane. And in this picture you can see the isoflurane unit as well. In fundamental and preclinical cancer research, intravital microscopy is important to study tumor cell invasion, metastasis, and tumor stroma interactions. However, tumors are dense and opaque, and this causes strong light scattering, which distorts focal spots and deteriorates the fluorescence signals. So this makes deeper imaging very difficult. Increasing the imaging depth requires higher excitation power, and this can damage the tissue. In densely labeled samples, also two-photon imaging depth is limited by out-of-focus background, so shifting the excitation wavelength from near-infrared to infrared reduces the light absorption and the scattering and can improve the imaging. By using even longer excitation wavelengths, so from 1300 nanometers to 1700 nanometers, and also higher pulse energies enabling three-photon excitation, the imaging depths can be doubled to 1400 micrometers, compared to the 700 micrometers depth that is achievable during the two-photon imaging with an excitation wavelength of 700 nanometers. So to obtain the three-photon effect, a 5 to 10-fold higher peak power is required to generate the same amount of fluorescence as compared to the two-photon excitation. So higher peak power is achieved by higher pulse energy while decreasing the pulse frequency. So the standard two-photon excitation is referred as low IR because it uses low peak power, short pulses, and high frequency, while the three-photon excitation is achieved with 1300 or 1650 nanometers, and it's referred to as high IR since it uses high peak power, ultra short pulses, and low frequency. In our lab, to longitudinally monitor the progression of the tumors by intravital multiphoton microscopy, cancer cells are implanted in the deep dermis of the mice within a dorsal skin fold chamber system. A dorsal skin fold chamber is an optical imaging window that is implanted on the back of the mouse, and it allows the in vivo inspection in real time. So in this image, you can see the nuclei of HT1080 double color fibrosarcoma cells that are invading collectively into the mouse dermis. As you can see, they are following the path of least resistance, which is the interstitial space within the myofibers, so they're following the natural tissue tracks. So, when applied in this tumor model, multicolor labeled HT1080 tumors in the deep dermis, the excitation with 1300 or 1650 nanometers, the latter in this case, produces multiple signals from fluorescent proteins. These in parallel together with the second and the third harmonic generation signals. So these multi-channel images reveal a detailed inventory of the tissue composition in real time. Fluorescence shows nuclei and cytoplasm of tumor cells. With Hexed staining, also the endothelial and the stromal cell nuclei become visible, and the blood vessels contain the Alexa Fluor 680 conjugated dextran, which is a vascular tracer, and the second and the third harmonic generation show collagen and red blood cells respectively. So this demonstrates the 3 and 4 photon excited fluorescence along with the second and the third harmonic generation signals were able to be captured at the same time using one single laser excitation, the 1650 nanometers in this case. So it resulted in a 6-channel image in a single scan, and this avoids the chromatic aberration from imperfect laser alignment, which is a common issue in multi-beam imaging. Deep tissue microscopy resolution depends on scattering and beam aberration, and this varies with the wavelength. So to compare low versus high pulse energy excitation, the same tumor area was imaged at different wavelengths. 1180 nanometers and 1300 nanometers and 1650 nanometers. 3 and 4 photon excitation resolved subcellular features in EGFP and TAGRFP labeled cells, even after 400 micrometers of depth, while the 2 photon excitation reached only 225 micrometers. So resolution in 3 and 4 photon remains higher at greater depths, as compared to the steep decline in 2 photon excitation after 125 micrometers. And this makes the 3 and the 4 photon excitation better for imaging in scattering tissues. Using high pulse energy for high IR excitation has pros and cons. On one hand, it enables multimodal excitation, but on the other, it can also cause physical damage, toxic reactive oxygen species, and photobleaching. The heat buildup can also lead to phototoxicity. In this study, intracellular calcium responses in tumor cells expressing the calcium sensor GCAMP6 were used to measure the cell stress. These responses indicate non-lethal stress from the calcium channel opening or the membrane damage. So to determine phototoxicity thresholds, the mouse dermis tumors were exposed to 1300 and 1650 nanometers excitation, and their calcium responses were monitored. Small changes in power density can significantly impact the results, so a careful benchmarking is very crucial. and the calcium responses show signal increases before even any visible damage, so this really helps to establish a safe power density for multimodal excitation without causing phototoxicity. So, to recapitulate, high IR excitation allows simultaneous 2, 3, and 4 photon processes with one excitation beam, covering blue to deep red within the same focal plane, up to twice the imaging depth in the tumor tissue, and a fine balance between sufficient signal to noise ratio and nonlinear photodamage in the focal plane. So models with brightly expressed fluorophores would benefit the most from this.